Hello, friends, and welcome back to Machine Learning with Cats, Part 2. It is so good to have you here. My name is Will. I will yet again formally introduce myself in a few minutes, but it's great to have you here. Hello, Micah. Micah, good to see you. Good to see you. Thank you for filling out the feedback form and leaving a comment on our discussion thread. Ohio, Bhavya Pratap. Oh yeah, okay. If this is where you're calling or where you're joining Twitch from, let me know. Yeah, drop in the comments where you are and what the weather's like. I'm in Seattle, and it's sunny. Oh, we have two folks in from. Wait, oh sorry, Micah. Are you in Ohio or in Seattle? Also, as always, our machine learning track question: what is the last beverage that you had? I actually very recently had some Earl Grey tea at work, and now I am back home. Just recently got back home and drinking some water. Ohio is representing. We love to see it. Good deal. Well, I'm very excited for the stream today because we are going to check back in on everything, of course, get an update. But then we're going to just dive in and get our hands dirty and write our first machine learning algorithm just to sort of hit the ground running. Technically, we did submit the other day. We just submitted the default submission thing. But so today we're actually going to use our data to make predictions, which is, of course, the heart of machine learning, or at least the heart of supervised machine learning. And then we are going to dig into our image data. So yesterday we learned a lot about Python. That was sort of our reintroduction to Python. But now today we're actually going to look at the images that make up our data set because we didn't really touch on that yesterday. So we'll learn a few tools that we can use to mess around with images, and that should hopefully set us up to both have some solid machine learning predictions today, but then also set us up to do some more powerful stuff tomorrow. Let's see what else. Oh, okay. So thank you to everybody that filled out the feedback form yesterday and voted. We have our selections. So the top, let's see, it was the top 5. So this week we're voting for what color glitter I put on my face for Friday. And the top 5 answers were blue, silver, blue, green, red, and purple. And so those are the 5 options for voting today. Let's see. We got some great feedback. Most folks felt like the session was pretty good pace. There are a few folks that were like, hey, like that was a lot of beginner stuff. Can we speed it up? And there were some folks that were like, hey, you know what? I kept up, but it was kind of fast. So we'll probably keep things about the same. I will say that if you were feeling like, hey, this is all intro stuff, it's the first day. It was literally intro stuff. But we will, I think I mentioned today, we pick up speed a little bit. And then tomorrow through Friday, we will be getting sort of more advanced every day. So we'll definitely get there if you felt like it was slow. We didn't have a ton of questions. We had lots of positive feedback, which we love to see. And then one person had a question: can we train models like ChatGPT for specific use cases on Kaggle for free? And the answer is absolutely yes. I have done it. Now a couple finesse points here. So if you did not join us for our last session, Kaggle is a machine learning platform where you can both build and train models. And something like ChatGPT takes hundreds of GPUs over months to get the final model weights of that kind of model. But a thing that is very, very common in large language models is called fine tuning, where you take a model that is mostly trained and you just take it the last couple steps, right? So maybe it is, you have a model that basically understands English and you just lay on top of it a lot of data about biology, and you fine tune that big large language model into something that's particularly good at biology. And this would be totally a thing that you could do inside a Kaggle notebook. So you can, I mean, you can do any of these things, but from the perspective of how many GPUs do you get and how long do you get to use them, training a big model from scratch, I think, is going to be a really aggressive goal. Whereas taking a model that is mostly trained and fine tuning it is super viable, which is something I've done. Which, if you're interested in that, let me know in the next feedback form, and maybe we plan that for next Global Hack Week. Maybe we do a little train your own LLM. Hello, Palak. Good to see you. Happy Tuesday, or is it for folks in India? Is it Wednesday? I know it's early for y'all, but no, we're on the same side of the. Let me know if it's Tuesday for you. Actually, I don't even know if we have anyone from India in the chat. I know yesterday we did, and I was very impressed because it was like 5 a.m. for them. I guess we'll get into it. So hello, my name is Will. I'm a software engineer at Google and a coach at Major League Hacking. I am very into machine learning and Python and cats. And today we are going to be jumping back into it. So yesterday we did an intro to Python. And so if you didn't attend yesterday, but you do understand some Python, then you're in great condition. If you did attend yesterday, then hopefully you've refreshed your Python and we can hit the ground running. If you are tuning into this stream and you have never touched Python at all, I will not lie to you. This will feel a little bit fast. But you're still welcome to stick around, and we will work through things. Okay, Hamna Reel is from Pakistan. What time is it for you? I'm very curious, because I have a feeling it's probably like, I don't know, like 7 a.m. or 6 a.m. or something. All of which are very impressive to me. Good deal. So this is our. I guess we'll do all the links. If you are here, you should register for the event. Oh wow, very early. Yeah, I will confess, I do not get up that early. So here is our check-in link. And then here is, of course, our competition link. So if you weren't here last time, most of our sort of event revolves around this Kaggle competition. If you don't have a Kaggle account, it is free. They will never charge you for anything. And it is actually you get a lot of stuff for free. You get a lot of GPU time for free, which is really cool. And that is where we're going to be sort of doing most of our work through these Kaggle notebooks. So to refresh on what our task is, if you click over to the data tab, if you click into images, we should actually be able to see the images. Here, you can see we have a bunch of images of crypto cats or crypto kitties. And these are NFTs. And an NFT is a non-fungible token. Someone actually asked in discussion, is an NFT crypto? And I think a lot of words have fuzzy meanings. So crypto kitties are not cryptocurrencies, but they are crypto assets. They are non-fungible tokens that are based on a blockchain. And so I think that's the distinction. They are crypto, but they're not a cryptocurrency. And the reason is that every crypto kitty is different, right? So dollars and Bitcoin are fungible. Every dollar is basically identical to every other dollar. There's no reason that you should prefer $1 to another. In the same way that you would never prefer one Bitcoin to a different Bitcoin. They're exactly the same. Sure, they might have a different serial number on a dollar bill, but there's no reason to prefer one to another. Compare that to paintings, right? A painting holds value, but it's not a currency. It's, you might have one painting, and if I stole your painting and gave you a drawing that I did in crayon, and I was like, hey, you started out with one work of art and you have ended here with one work of art, like, why are you upset? We would all be like, well, clearly they're upset because you can't just swap one painting out for a crayon drawing and say you're fine. We have reasons to prefer one work of art over another work of art. And so that is what an NFT is, a non-fungible token. And I think the idea of thinking about NFTs sort of in relation to art can be a pretty useful way to understand them when you're getting into them. So CryptoKitties are an NFT. Each one of them is different, and you might like one more than another. So we can just click through our images right here, and they're all unique and distinct and gorgeous and beautiful. And I'm really quite fond of all of them. And so our goal in this track is to look at this image and predict how much someone is asking for to sell this CryptoKitty, because of course you can buy and sell these things with Ethereum. So that's our task, is look at this image and predict how much it's going to sell for, or how much someone's asking you to pay for it. Let's see. Palak said, I tried to do this based on test and train, but failed. Interesting. If you were digging into the notebook that I posted yesterday, we'll look at that and we can walk through any problems you have. Otherwise, I might need more details to understand sort of what issue you're facing. But so these are our CryptoKitties. And the thing we're going to work towards is building a machine learning algorithm that can look at one of these and predict what it's going to sell for. And we can see that actually, I think everybody, or lots of people, went and filled out just the, or submitted the default submission. And this is just if you said everything sells for 0, right? You're allowed to make whatever guess you want. And if you just always guess 0, then this is the score you get. So what does this score mean? Well, this score is the mean absolute error. So on average, our predictions were this wrong. If you just say 0 every single time, then on average, you are 38 Ethereum away from the right answer. And I think we did this conversion. If we have this many Ethereum to US dollars, I don't know if you can see that. We'll zoom in. We are on average $63,000 away from the right answer. So if you asked me, oh, hey, Will, how much is that bike worth? And I said, $64,000. And you're like, Will, that bike is only worth $100. And I said, I was only $63,000 off. You'd be like, that's ridiculous, Will. That's not a good prediction. So that's where we're sitting right now, but that's okay. We don't actually have any machine learning yet. And so that's our first step today, is going to be to dig in and write our first machine learning model. So without further ado, let's click over to code. And oh, actually, before we get going, I wanted to one more time refresh on how you can win a swag drop during this stream. So we're going to be doing 5 swag drops, and the first 2 will just go to anyone who is the first or second sort of on the leaderboard. So obviously, right now it's a 15-way tie, but hopefully over time we'll get better and we'll have a first place and a second place. Bhavya says, I'm not familiar with Kaggle's workflow. Am I good to go? Yes, I will say for all the parts that you will need to interact with, I mean, one, I would say sign up for a Kaggle account now, so that when we actually get into the notebook, you can just follow us along. But yes, even if you've never used Kaggle, at this point, you're still okay, and we can cover all the things you need to learn. So the first 2 swag drops are just going to go to first place and second place. The third swag drop is going to be randomly selected from somebody who made a submission who is a contributor. And the way to know if you are a contributor is to, if you zoom in, if on your icon there is a little, I think that's blue, and it's sort of 2/5 of the circle is full, then that means you are a contributor and you are eligible for the raffle. If your icon looks like this, you are not a contributor yet. Which I think Spirit there are only 4 things you need to do to be a contributor. One of them is run a notebook, which everyone has done. One of them is make a submission, which if you're here, you've done. And then the other 2 are give an upvote on something. So you can upvote any comment or notebook and make a comment. And so if you are not a contributor yet, the thing I'm inviting you to do is you can just go to this discussion and just say hello to me, and I'll say hello back. And if you said hello to me and I haven't said hello back yet, I will get to you and I will say hello. But you can click over to discussion and just leave a comment here. And after that happens, you should be upgraded to the level of contributor. And this is just a way of fighting spam and bots and making it so you can't sign up for 1 million accounts. So that is what we're doing there. So those are the first 3 ways to win a swag drop. We have the first and second place, and then a random raffle who is a contributor, and then the best code published. So if you come over to code, whenever you write a notebook, you can publish it if you want. You don't have to make it public, but you can. And then, it's taken a second to load. Okay, so you can publish your own code. We have one notebook published by it's not Pramila? Is that how you pronounce the name? Marilia Prata. And then the final way is by having a really good discussion. So if you have a discussion and it gets engagement, someone will be selected there as well. But so on that note, once I respond to some questions, we'll dig in and start building our first machine learning model. Hello, MLH community. Oh, hello, Tintin. I'm doing well. The session today, we are going to build our first ever machine learning model, at least for this track, and we're going to do some pre-processing of our images and learn about image data. That is sort of the broad plan for today. Palak's on top of it. Yes, I think these are basically correct. Yesterday we did Python and some libraries. The libraries we learned about were pandas and matplotlib were really the big ones we touched on. And then today we're going to learn about machine learning algorithms. Yeah, and particularly we're going to learn about linear regression. Let's see. Vaskar MV says, does the forecasting algorithm take only previous price as input for the prediction, or does it take into account stuff like picture aesthetics, artist name, season of NFT launch, etc.? Yes. So this is a great question. So all these are really, really good questions, and the answer is everything for this competition has been made very specific just to make it sort of an easier problem for us to deal with. So we are not looking at all of NFTs. There are, I'm sure at this point, trillions of NFTs out there. We are just looking at CryptoKitties. So if you click back over to data and you go into our images, all of our NFTs are the kitties. Does it take into account stuff like picture aesthetics, artist name, a season of NFT launch? So the data for this I got recently. I won't say exactly when, but it was recently. And all of these are Gen 0 CryptoKitties. And the number that we're trying to predict is that the price that the current owner is asking for them. Okay, I'm going to take the as a good sign that you think the CryptoKitties are cute, because I also find them very cute. Yeah. So our images are just a bunch of these adorable CryptoKitties. So there are a lot of limitations here, right? We're not going to use this to predict any NFT's value, and we're not even really predicting the value. We're just predicting what is a person asking for it. So, I could say, hey, I'll sell you my house for $2 million, but my house is not worth $2 million. And so me asking for $2 million does not actually make it worth that much. So a lot of good caveats, but great questions. Okay, cool. So then without further ado, let's click to the code tab right here. And then, I guess I'll revamp this. So part 1.5 is just submitting. So if you click on this right here, I see this screen. You should see a button that says copy and edit. And if you click that, you will basically create a copy of all the code that I wrote. And you can X out here to give yourself a little more space. You can press this button down here to bring it back. But so this is a Kaggle notebook, and you can press play to run an individual cell of code. So you can code up in these little cells. You can always press plus code for more code cells. And this bit of code right here, all that it's doing is it's importing pandas. It is right here. It is reading our inside our data set. We have a sample submission CSV just to show you what it's supposed to look like. In fact, I'm gonna bring down the size just a little bit because this is a little big. So here we're just reading that CSV at this file path, and then we're just rewriting that same file out to a file called submission.csv. So we're saying whatever the sample submission is, I just want to use that. And when you have a notebook that creates a submission.csv file, that means that you can submit this notebook and be entered into our competition. We'll look a little bit more at exactly what is in that file later today. But just for the purposes of getting off the ground running, at this point, if you've copied this file, you can click submit, and you will show up on the leaderboard, and you will be entered into the raffle and all of those things. So this is sort of the quick intro into Kaggle if you weren't here yesterday. So now we can click back to how much would you pay for a fake cat. This is our overview, and click back to code. And now I want us to go to part 2. So that was part 1.5, just getting a submission out. But part 2 is where we actually get to do some machine learning. So CryptoKitties have lots of cattributes. If we actually go to cryptokitty.com or cryptokitty.co, which I'll drop a link in the chat just cause. And if you go to the catalog, and maybe click over just on CryptoKitties. If you click on, here's just not that one. If you click on a random CryptoKitty and you scroll down, you can see it has lots of different cattributes. So Himalayan fur is just this fur pattern here. And I think if we click on it, we can see other CryptoKitties that have the Himalayan fur pattern. Maybe that's the color, because that all looks. Oh, I bet the Himalayan fur is sort of like the shape of the fur, not the pattern. Okay, yeah, because pattern. So this is the jaguar pattern, and if we come over here, okay, yeah. So all of these cats have the jaguar pattern, which makes sense. Good. And you can see they have different eyes. So there are lots of these different attributes that cats have. But all of the cattributes show up in their image, right? There's one sort of important piece of data that doesn't show up, which is their cooldown. So basically, every time a cat has a baby or a cat breeds with another cat, it slows down a little bit. So before it has ever had a child, it is, I believe, swift. So swift is like the fastest you can be. And every time it has a child, it gets a little bit slower. It gets a little bit older. It gets a little bit slower. And this is one attribute that I suppose, if you're into collecting CryptoKitties, you care about. There might be some sort of some unhealthy purity norms baked into the system, but this is the system as we understand it. And so speed determines how fast a cat can parent additional kittens, and so it's something that might make our cats valuable. So I want us to kick off. I'll click edit here. You can click copy and edit, and I'll just drop this. If you just want to join along, this is where we're at right now. And so to start out, let's import our libraries, pandas and pyplot. And then we're going to import both our training data and our test data. So if you click over here, we have train.csv and test.csv. And if I run this cell, we'll import them both, we'll read them both, put them in variables, and then remember train df head. This just shows us the very top of our training data set. So what do we have going on here? We have an ID. So every cat in our data set has an ID. Every cat has a price. So this is in Ethereum. So this is 2.13 Ethereum. They all have a speed that's like this string, but the string also contains a number. And then we have an image. So this is the name of the image for this cat. So if we wanted to, so 7D46, it might take a very long time, but we could. Oh, never mind. Okay, yeah. So this file editor is not the easiest if you have a bunch of files. But imagine this said 0068810. We could click on here and okay, that's our cat. So our table here is related to the images. Any questions just right up front about like how this CSV or how this training data set, how this works? We have the ID, we have the price we're trying to predict right here. The main piece of data we have is the image and this path over here, but then speed is also this relevant factor that we might want to consider. So first, let's look at the thing that we're trying to predict, which is the price. So we can hit play right here, and you can see we have, a bunch of individual numbers. Okay, Palak asks, how are we going to use the image? Great question. We are going to get there. We will touch on it today, but then tomorrow is when we really get to use images. We're going to build sort of a simpler version of a machine learning model today, just to kind of get off the ground. But then later today, we'll look at messing around with our data image. Later today, we'll look at messing around with our image data. And then on Wednesday, tomorrow, we'll see how can we actually use the image data to make better predictions. Let's see. QTexRJ said, hi, I just joined what we want to do with Kaggle. Yes, so if you are just signing on, Kaggle is a machine learning platform, and it is the place that we are all coding up our machine learning algorithms in order to predict the value of these cat-based NFTs. So in our images here, you can see, oh, if we scroll up maybe a little bit, you can see our pretty cat just kind of peeking out there. And I'll say you're kind of joining in 20-ish minutes late, so you might have to play a little bit of catch up. But you are so welcome here. I will drop here is the link to the Kaggle competition. And then this is the individual notebook that we're working on right now. And so we're going to look at lots of different algorithms. So today we're doing linear regression just to kind of get started. But in the future, we're going to look at sort of dense neural networks, but we're also going to learn about convolutional neural networks. And we're even going to do some interesting GradCam sort of explainability models where we'll actually be able to visualize what is the network looking at when it makes a particular determination. So like, what was it paying attention to that made it think this cat was worth a lot of money, which would be sort of an interesting thing to look at. I apologize if I'm getting ahead of myself, but are we learning PyTorch or TensorFlow this week? Yes. So most of the week will be in TensorFlow. Today is the last day that we're not using TensorFlow. I like PyTorch. I actually just need to learn more about PyTorch because I'm pretty good with Keras and TensorFlow, and I am basically a noob when it comes to PyTorch. But I think PyTorch is really cool. Cool. So we have a bunch of data about price, and in addition to just seeing that we have a bunch of numbers here, we can also see that the data type here is object, and that's a little bit weird because the data type that it looks like is a float, right? It's like a number with a fractional part. And so like, why isn't it a float or, or even an integer? I don't know. And the answer is kind of hard to see here. But if we look at, I wonder if we just look at a greater range, if we'll see something. Like, what if we just looked at the first 100? Oh, it's going to cut that off too. Okay, what if we looked at 10 to 100? It's cutting off a lot, but the thing that's going on here is that these numbers have commas in them, and Python does not like reading numbers with commas. So if it's like 9,000, if it's like 9,000 Ethereum and it's spelled like this, Python's going to be like, oh, okay, well, numbers don't have commas in them, so that's obviously a string, which is a little bit silly, but that's what it does. So one way that we can handle this is we can write a function to clean up our price data. This is sort of well, I don't say it's little known. I think it's widely known, but the sort of unsexy part of machine learning that you have to spend a lot of time on is just cleaning your data. And once you have done all of sort of the grunt work of cleaning your data, then you get to make the magic happen by deploying the super neat machine learning algorithm. So we'll do a little bit of data cleaning here that we'll walk through. Bhavya mentions, I've worked with binary classification with neural network. For image classification, are we going to use some other algorithm tomorrow? Okay, yes. So you're getting a little bit ahead of me, but this is something that I do want to talk about is the fact that what we're doing here is kind of weird. So today we're just going to be doing basically sort of tabular regression. We're going to go from just our table of data without looking at the images, and we're going to try to predict a sort of a number, a real number value that could be anywhere from 0 to infinity, technically. And this is actually kind of a rare thing to do with images. So if you think about the major classes of machine learning, you have things like unsupervised learning, like clustering. But then with supervised learning, well, okay, actually, random poll question. If I say supervised learning versus unsupervised learning, can you in the chat give me a yes if you know what those things are, or give me a no if you do not know what those things are? Because everybody is familiar. I don't want to spend like a bunch of time covering it, but if this is a thing that folks are less familiar with, then like I would love to spend a second just sort of unpacking supervised versus unsupervised learning. Okay, great. We got a couple of no's, and so I will run through that a little. We got a little. Oh, me, Mr. Mustard. You were on stream like a while ago, right? I remember you. It's good to see you again. A little Um, so, okay, so we got some yeses too. So if you know, sort of hang with me. So in machine learning, there are a couple of big classes of sort of methodology, of ways you can do things. And the sort of the basic one that most people start with is called supervised learning. So that is where you have basically some questions and some answers. So maybe the question is, based on this image, is it a dog or a cat? And the answer is either dog or cat. And whenever you have a bunch of labeled examples like this, where you have, image and label, or maybe it's details about a house and how much that house sold for. So details and sale price, details and sale price. Anytime you have that sort of setup, it is a good chance that you are looking at supervised or an instance of supervised machine learning. And this is the idea of you show your model a bunch of labeled question answer pairs, and it learns how to go from the question to the answer. So that is supervised learning. There's a thing called unsupervised learning, which is usually like you're trying to figure out something about your data without really coming up with an answer. So a classic example of this is clustering. So imagine you have 1,000 customers, and you have details about them like like their age and their height and how much money they spent and where they live. And you want to group them into clusters, into little groups, so you can say maybe you send a lot of coupons to one group, but you don't send coupons to another group. Maybe this is a case where you don't really have like a question answer. You just want to figure out some structure inside of your data. And so this is a case of unsupervised learning. You can also think of creating word embeddings. If you're familiar with word embeddings, that's a thing used by ChatGPT, is just a number that represents a word really well. Creating word embeddings is an example of unsupervised learning. And then the last category that people often throw out is reinforcement learning. And it's sort of the redheaded stepchild here. I mean, reinforcement learning is basically creating a model that can interact with an environment. And whenever a model can interact with an environment and basically create its own data, so it can try something out and see if that worked, and iterate from that, that is reinforcement learning. In fact, actually, let's pop back in here because I want to write down some notes. So we have supervised learning, which is labeled questions and answers. We have unsupervised learning, which is sort of learning some structure about our data. Like an example is sort of customer segmentation. And then we have reinforcement learning, which is learning from interacting with an environment. So like learning how to play chess is a great example. And so supervised learning is what we're doing here. But inside supervised learning, there are two sort of big groups of supervised learning task, which is classification and regression. And because I've done quite a bit and written some stuff down, I'm going to check back in with the chat. We got some yeses and some nos. CuteXRJ says, I just want to ask a thing. So if we are doing this model, will it get deployed on blockchain? No. So we are not actually deploying anything on blockchain. We are not actually using Ethereum. The only thing we're doing is we're just looking at the images of NFTs and predicting their price. So this is, I think this stream, it's related to the theme of the week being Web3 only in the most vague way, right? Like the thing we're doing machine learning on is, stuff that's on a blockchain, but we're not directly interacting with the blockchain. Yes, Mr. Mustard, you have a very memorable username, which is the reason that I remember you. Let's see. Not gonna lie, I enjoy your sessions the most as I skipped my not so important class just to attend this event. Oh, okay. Well, on the one hand, you shouldn't skip class, but I am touched that you are here, and it's good to know that you're enjoying it. So these are our big types of machine learning: supervised learning, unsupervised learning, and reinforcement learning. And then within supervised learning, we have these two categories: classification and regression. So classification examples include sort of like, is it a cat or a dog? Or part of speech tagging is technical classification. So like, is this word a noun, verb, or adjective? You always have sort of a couple options. You can even think of, does this patient have cancer? Which would be, yes or no. Regression. So all of these, you're trying to predict, does it belong to a particular group? But with regression, you're trying to predict a number. So for example, you could predict what score will I get on a test? You could predict how much will this house sell for? I can spell. How tall will someone be when they grow up? So all of these questions are regression, and all of these questions are classification. So someone mentioned binary classification, which is just a kind of classification where you only have two options. So actually, the first one and the last one, is this a cat or a dog, or does this patient have cancer, are both binary classifications. And an interesting thing happens when you look at different kinds of data. So sometimes you're using text data, sometimes you're using audio data, sometimes you're using image data. Sometimes you're using tabular data like a spreadsheet. And an interesting trend in image data is that almost always, like it's very, very likely that if you are using image data, you're doing some kind of classification, right? Just because there are so many things in images to classify. You could classify, is this image, like, is there a dog in this image? Is this an image of, I mean, if you've ever played, or not played, if you've ever had to do a CAPTCHA, this is essentially an image classification problem, right? It asks you to pick like which of these images have a sidewalk in them, right? And what we're doing is really regression, right? We're not actually trying to pick one thing or another thing. We're just trying to predict some number on a scale, and that number could be, anywhere from 0 to infinity in theory. I know this is a little bit of a tangent, but this kind of sets us up for understanding what we're doing here. So today, we're going to dig into cleaning our data and building a linear regression model, which we'll understand a little bit more about what linear regression is in just a second. So here, we're writing a function that will just take in, to recap, these numbers sometimes have commas in them. And so we can write a function to take in that string that sometimes has commas, remove all the commas, and then return the actual number so it turns into a number. So for example, if I just copy this up here and I say clean price, so the first thing we do is we just say replace all of the commas with nothing. So we're just removing the commas. And then we're returning that price turned into a number. And so we can say clean price of 123. This should just give us 123 as a float. But then what if we say 1,123 and we still get that number? So it gets rid of the comma and it just turns it into a number. This is actually maybe silly, but if we said, okay, yeah, int doesn't like commas, right? Can't we use rstrip func instead? So my understanding is that rstrip will only take preceding characters. We can check. Let's see, rstrip Python. Removes any trailing characters at the end of a string. Yeah, so this wouldn't work for us. I mean, we can test it out just to see. But so if we say rstrip, so one option is if all of our random characters are at the end. Or I guess we'd call that on a string, wouldn't we? Yeah. So if we say 1, 2, 3, and we have a comma at the end of that, and we call rstrip with the comma, then we get what we want. But in the case where we say 1,123, it'll still leave it. Yeah, and so I believe strip only works on sort of the edges. Yeah, so it'll still leave it. But replace is sort of a quick and dirty way to clean it up. So we can sort of test this by passing it in 1,234.1, and it gives us the right float back. So now, because our numbers are no longer being interpreted as strings, we can use this function called apply. So apply just takes a function and then runs it on every single item in your series, and then gives you back the result of it sort of as a new column. So like a sort of dumb example of this would be, what if we just wanted to multiply all of our numbers by 2? Well, that wouldn't really work right now because they're not numbers. But what if we wanted to add hello to the end of all of our prices? Well, we could say, we won't use a lambda. We could say, define add hello as accepting a string or accepting text, and then returning our text plus hello. And if we run this, we have to actually pass it in. So this will say run add hello on all of our text. So here we see all of the text now says whatever it said plus hello at the end. So that's how apply works. We don't need that example anymore, but we're going to apply clean price. So this will clean up all of our price data, and then we can store what it outputs into a new column called clean price. So if we come back up, we can see we had, well, we don't really need to look at, yeah, so 2.13.0.46, but the data type is an object. And if we scroll down, we can see it still says 2.13.0.46, but the data type is a float. So that is progress. Pat yourself on the back. And so now that it's actually a number, we can visualize that data by creating a histogram of it. If we don't want this junk to show up, we can just say plt.show. Great. Okay, cool. So what's going on here? We're looking at this graph and it kind of doesn't make any sense. And the reason it doesn't make any sense is for one simple reason, because people are just randomly picking prices, right? This is like earlier I said, hey, what if I just decided I'm going to say I'm charging $2 million for my house? And like, yeah, I can say that, and I can go onto a listing site and say my house for sale, $2 million. But that doesn't really make that number very meaningful, right? And my number there is not going to be particularly useful to most other people. So what's happening here is a lot of people are saying relatively small numbers, but then there's one person out here that's charging a crazy amount for their CryptoKitty. So if you look at, it's 1 times 10 to the power of 6 is how to read that graph. And if I say 1 to the power of 6 Ethereum, so I guess that's technically a million Ethereum to USD. That is, what is that? $16 billion. They're charging $16 billion for the CryptoKitty, which, like, that's just not going to be very useful information if we're trying to predict other people's values, right? So what we can do is we can just say anything that's more than 100 Ethereum, let's just cap it and say that it's actually 100 Ethereum. And there's a super handy dandy function we can use for this called clip. So clip just lets you give it a range and say that anything below 0 or above 100, just squeeze into those points. I don't think we had anything. It looks like our lowest number is around 0. So there's nothing below 0, which makes sense. It probably isn't possible to charge a negative amount of Ethereum for a CryptoKitty. But if you're charging more than 100 Ethereum, maybe you're just, you've drunk the Kool-Aid a little bit too much, and we're going to chop that off. Now, I'm being a little bit cavalier about this. In practice, you might want to play around with this number and try different things out. You might want to, dig a little bit and see, like, well, what's the most expensive CryptoKitty that has ever sold? And maybe you clip that, right? But I'm picking 100 just as sort of a number that, another way of putting it is that most of our CryptoKitties are well under that amount. Most CryptoKitties are just really, really not being sold for that much. And we're really trying to predict most things correctly. And so if we're wrong at like the one dude up here, but we're right about all of the CryptoKitties down here, then maybe that's a trade we're willing to make. Anyway, that's why we're picking 100 here. And so we can clip our cleaned price and put it back into the column of clean price. And when we run that, we can say plt show again here to clean it up. We should get something a little bit better. Okay, so down here you can see there's a chunk of people that are charging, more than 100 for their CryptoKitties, but we can see it seems like a lot of sane people are kind of down in this region of maybe it's 0 to 10 Ethereum, maybe it sneaks up to 40 Ethereum. But then really quickly you sort of thin out. And you can see all of those people. This block is kind of big because all those people that were charging more than 100 for their CryptoKitty, they're all just becoming 100 now. Any questions about what we just did there? We saw that our graph was really skewed here, and we made a decision to just clip our data and say all the numbers greater than 100, just make them 100. So this is the price that we're trying to predict here. And so now let's take a look at the one piece of data we have that might be useful. If we scroll back up, ID is just a random ID number, and image is just that random ID number pointing to an image. But price and speed both have some information, right? Price is what we're trying to predict, and speed, we know that it's likely that cats that are faster might sell for more money, right? You might want a cat that is more fast. That might be a reason to prefer it. So we can come down and just like we did for price, let's take a look at our speed. So if we run this, we know, of course, this is also a string, right? It has text, but it also has this number hiding in there. So we have 1 minute is fast, and dot value counts just shows you how many of each value you have. So most of the cats in our data set, in fact, are fast. 1,067 of them are fast 1 minute. But then the next biggest chunk is 389 of them are catatonic at taking 1 week to be able to parent another cat. Then we have swift, and that says 2 minutes, and there are 97 cats that are swift. Then there are 76 cats that are swift at 5 minutes. So you might be, there are lots of different kinds of swift. You might be swift and only take 2 minutes. You might be swift and take 5 minutes. And I think that's true for snappy could be 10 minutes, or snappy could be 30 minutes, and so on and so forth. And so really the text is kind of interesting. I think the names are kind of funny. Catatonic is just like a really good pun. But really it's that information in the middle that we're interested in, and not just the 1 minute. Really, I'd like to get all of these to similar units, right? Because if I put in 1 week versus 1 minute, there's not a super intuitive way of doing math there. Whereas if I just convert the number 1 week into a number of minutes, then those are both sort of numbers of minutes that are easy to compare. So let's write a function that will take that string and pull out from it the number of minutes that is the cooldown time. And then we can, in theory, we can use that number of minutes of cooldown time to help predict what the price is. So regular expressions are a really, really useful way to interact with text and to manipulate and search strings. So we'll be using the RE regular expressions library. And I've gone ahead and created a dictionary or a map called unit map that just goes from a letter to how many minutes that represents. So M is for minute, and so there's just 1 minute. H is for hour, and so there are 60 minutes in an hour. D is for day, and so there are 60 times 24 minutes in a day, because there are 60 hours in a minute, 60 minutes in an hour and 24 hours in a day. And then a week at the low end here is 60 times 24 times 7. So this hopefully is not too complicated. This is just, converting different times between each other. Now this gets a little bit more complicated. So we're defining a function called clean speed. And this is going to take our speed string and return a number of minutes that speed string represents. So this function takes a speed string from our data set and returns the number of minutes it represents. So the first thing we got to do here is to find our specific string that we care about. So inside this whole string here, really the only stuff we care about is what's inside those parentheses. So this is a regular expression. So re.findAll, you give it a regular expression, which is a super kind of fancy esoteric way of searching strings. And then you give it a string you want it to search, and then it returns to you a list of matches. If you are interested in sort of unpacking this regular expression, I am willing to do that, but it's not really the main point of our session today. So I will only dig into that if someone in the comments says, "No, I'm very interested in regular expressions. Like, tell me about them." But the main thing you have to know is that this regular expression here will find all of the text inside of these parentheses, and then we'll get it in a list, and this list should only ever have one thing in the list. So we can just grab the first thing in the list with index 0 and then store that in our cooldown string. So the whole string is our speed string, but just that stuff in between the parentheses there, that's what we're calling our cooldown string. Okay, people are interested. I'll admit, I feel like I kind of knew that someone would be interested. Okay, so regular expressions. Let's actually pull up a regular expression playground. Regular expression playground. So regular expressions are a way of identifying different parts of text. So at the very simple level, can we pick Python? No, we can't. I think the Python and the JavaScript regular expressions are basically the same. So a very simple way of writing a regular expression is just literally writing the text you want to match. So you can see here, the regular expression ASDF just matches the text ASDF, right? But you can also do things like include little wildcards. So a period is a special character that matches, for the most part, any character. Oh, here we go. Any character except line breaks. So that makes it a pretty versatile character to use. But instead of, so we can right here, we're matching. Is this big enough? Let's make this even bigger. And here, I don't need a menu here. So here, these 3 dots will match anything, and then we have F right here. But what if because we have 3 dots right here, they're all the same thing. Here, let's pick a more interesting string than ASDF. Okay, because Polak and Bavia asked, we'll say Polak and Bavia. So I could say Polak Bavia, and that matches the whole thing. But I could come and I could just replace Polak's name with 5 dots, right? But if you use a bunch of repeated characters, a nice little thing you can do is you can just press plus. And so this means any number of dots. So it will match all of these number of dots and then a space and then Bavia there. Another thing that you can do is if you only want to match things that are part of like a set of characters, you can use square brackets to create a character set. So here I could say PALK because the A is sort of reused, and so we can match all of the name just by saying these are all of the letters that could be in Polak's name. So these are some basic things you can use here. You can also use, now if I'm going to jump back just to see what things do we really need to explain. Okay, yeah, if you want to match just characters, so what if I had some numbers over here and then some numbers over here? I could delete all this, and I could say, okay, match all of the numbers 1, so we'd match 1 and 1. But what if I just want to match all numbers? I can do \d and then a plus sign. So this is the \d refers to all digits, and the plus says 1 or more of that preceding token. So \d plus means any consecutive group of numbers capture that or match that. The final thing you need to know about is a thing called capture groups. So a capture group, you just put in parentheses. And this basically just says, I want to select out the data from this. So this is sort of more useful when there's something that you want to match otherwise. So what if we had, what's some good data to make up? What if we had a bunch of records for Polak and Bhavya. So let's say I had Pollock and Bhavya take some tests, and they mostly get 100s, but then occasionally they get still very high grades, but not 100s. And what if I just want to match? I just want to grab all of Pollack's grades, and I want to filter out Bhavya's grades. So what I could do is I could say Pollack colon space, and so now I'm getting the whole line. But if I only actually want to select out the number itself, then I can put parentheses around this, and this ends up capturing just this information. And so while we match all of it, there should be a way that we come down here. Okay, yeah. So we see capturing group 1, and it is just going to grab just the digits there, and then we should have a second captured group. Oh, yeah, we have the captured group there. And if we click on this, do we get to see what gets captured? Maybe I actually need to zoom out a little bit. I'm not sure how this little internet interface implements this, but this basically makes this a little unit that we can now pull out. That is your very, very like. There's so much to regular expressions. I mean, like you can spend literally 2 semesters of college just digging into regular expressions, but they can be a super useful tool to have under your belt if you're manipulating a lot of text. So if we come back here, we have most of the tools to understand this. It's a little bit messy because we have some parentheses that we're using for capturing, but then we also have parentheses that backslash parentheses just makes that it's like just a regular parentheses. And then we have our backslash D because we want to capture all of the digits. So like 2 or 24. And then we also have a character set of M, H, D, or W. So it's just going to be one of those 4 things, and we want to capture that as well. That is your crash course into regular expressions. Hopefully that was useful and not too much, not too nerdy. But this is our way of just really easily grabbing out just the relevant part there. Yeah, actually, if you're interested in NLP, regular expressions can be super, super helpful. Yeah. In fact, we can actually just test this really quickly. So we need to import RE. And instead of speedster, we can say random text, but then in parentheses, 123 hours. And so hopefully what we get out of this is just this 123 hours part. And there we go. It successfully grabs out just 123 hours. So it looks like our regular expression works. Cool. So cooldown stir now has just the, in fact, we can add a comment here. At this point, cooldown stir looks like, we'll use an example from up here, like 24 hours. How about 24 hours. So what we want to do is we want to first just pull off everything but that last little bit there. And so we can do that with a slice. I actually don't know. I don't think we talked about slicing yesterday. So I'll do slicing really quick. If we have a long string, you can slice it by putting a colon inside the square brackets and putting in your start and the place you want to start and stop. So if I want to start at the beginning, I can say 0. And if I want to stop at character 2, I can say 2. And there we go. We get 1 and 2. But fun fact, if you are going to start at 0, you can just omit it. If you want to start at the very beginning, you don't even have to write anything. So we get 1, 2, and then we leave out the rest of it. We can also use negative indexing. So if we want to say go up until the last thing, you can just say colon -1. And so that gives you everything but the last thing. So hopefully that is a good enough quick refresher on slicing. So this grabs us all of the numbers in here besides that last letter, and that's our cooldown count. So now, if we want to grab everything or just the last character, that's our cooldown string. So that basically tells us the unit. then we can do just indexing -1. So in the same way that, oh, I already got rid of our example. In the same way that if we go stop at the last thing, if we just replace that by just grabbing the last thing, we get 5. So now we have our count and our cooldown unit. And now we can just take our unit and get whatever we need to multiply by from our unit map. So if we pulled out M, then we'll just multiply by 1. If we got H for hour, we'll multiply by 60, and so forth. And so that gives us the thing we want to multiply by, and then cooldown count gives us sort of the original number. And we multiply those two things together, we should get our clean speed. So I'm going to run that, and before we look at it, I'm just going to try clean speed out just to see if it works. So an easy one is putting in this string, and we would expect it to just say 1. Cool, it works. We just got 1. Now, 2 minutes, that's pretty easy. That should be 2 times 60, so that should be 120. Let's see if that works. Oh, no, we got... Oh, wait, sorry, we're measuring in minutes, so that should just be 2. If we said something like 4 hours, then we would expect it to be 4 times 60. Should be 240, I think. Is that right? 240, boom. Love how you wrote that clean speed method in 4 lines. I wrote a similar method for a Java project once. It took me so long to get it right. I totally feel you on that. This is actually one of the things that, well, first of all, I appreciate the compliment. But this is one of the things that I love Python for, is that it's possible to do something like this in a relatively small number of lines. In fact, if we wanted to, we could have done it in 3 lines, but there comes a point of diminishing marginal returns, you know? Yeah, Java, I think, is sort of a uniquely sort of wordy programming language, but hey, it's very popular. It's very portable. You can run Java on anything. Well, that's not true. You can run Java on a lot of things. Great. So now we have applied our clean speed function to our, oh, now we can't see, to our original clean speed. Sorry, we're applying our clean speed function to our original speed column and putting it into a column called clean speed. And this looks about right. Now, it's a little bit interesting because it's like, oh, we have a lot of 1s and a lot of 2s, and then we have a 10, and then we jump up to 10,080. And this is just sort of the nature of the way they set up cooldowns. Is it doesn't have, you don't go from 1 minute to 2 minutes to 3 minutes to 4 minutes. You go from 1 to 2 to like 60, and it sort of, it increases non-linearly, we could say. But we're in integer 64. And now let's visualize that. Let's make a histogram of our cooldown times. Okay. And okay, there you go. This kind of matches what we saw up top when we were just looking at here. Like there's a lot of fast things and a lot of catatonic things. And then it kind of, progresses more normally. So we have a lot of fast things right here, a lot of catatonic things, and then some stuff in the middle there. So one thing we might want to do now is to try to visualize the relationship between these things. What does a change in one of these things mean for a change in another thing? Or where do most things tend to show up? And so this is just going to create a scatter plot of our speed and our price. And here I'm just making the color a little bit transparent. I also want, let's see, I want the tooltip actually. I think S is for size. So what if we said S equals 20? And let's say plt.show. Okay, let's make the size even bigger actually. Let's say 40. Okay, I want it even bigger. Let's say 50. Okay, that looks good. So this is our graph. On the x-axis, we have how many minutes it takes to cool down. And then on the y-axis, we have how much it's worth. Now, I don't know about you, but this graph, I don't get that much out of this graph. I mean, let's just to be a good computer scientist, let's add some axes. So the title is cooldown versus price, and then we can say PLT X label is cooldown minutes, and then Y label is price in Ethereum. Cool. So we have our labels now. So what do we get from this visualization? Well, there are a couple of things that we get. I apologize. I'm going to make the square or the markers even bigger. I just really like big markers. Okay, I like this better. So there are a couple of things that we can get out of this. I mean, one is that there aren't really at this point a lot of outliers. Now, of course, we squished a lot of the most expensive things down. So if we hadn't done that squishing, you would probably see some prices even higher, or you definitely see some prices higher than this. But you don't see any cooldowns further out than about 10,000 minutes. That's kind of interesting. You also don't have intermediate values. So it really does. It looks like after the first little bit, it consistently doubles. So this point is about double of what this is, and this point right here is about double what that is, and then this is really double what that is. So you get an interesting sort of exponential curve there, or exponential increasing. And then I guess you can see that there are just most things are fast. Just most of our CryptoKitties are fast, but also most of our valuable CryptoKitties are fast as well. And you have a lot of slow CryptoKitties that are not the most expensive ones. And that is, I mean, it's a little bit hard to see that, but those are the things that I would get from this graph. But because it's a little bit difficult to visualize, just because of the data doesn't really lend itself to a scatter plot here, there's just so much overlap. One thing that we can do is we can just take the correlation coefficient. So if you've taken a stats class, you will know what the correlation coefficient is. It technically tells you the percentage of variance in one variable that can be explained by another. But sort of the easier way that I would throw out to use it is to basically think of it as if the correlation coefficient is positive, it means that as one of these things gets bigger, the other one gets bigger, so they both get bigger together. And if the number is negative, it means that as one of these numbers gets bigger, the other one gets smaller. So we can just run on clean speed. We can do .core, so that gives us core for correlation, and we can feed it in our clean price. And if we run this, we'll get a correlation coefficient. And so we get negative 0.11. So this is a negative correlation, meaning that as one of these goes up, as your cooldown increases and you get slower, your price probably goes down. And as your price goes up, your cooldown probably goes down. But it's not super strong. It's not weak, It's usually correlation coefficients of like less than 0.1 are like, is that real? There's more than 0.1, but it's not, it's not negative 0.8, right? Negative 0.8 would be like a really, really strong correlation, negative correlation. But so this is a sort of a weak negative correlation. To add that closer it is to zero, less relationship, I believe. Is that true? I suppose that technically is true. Yes. I don't think it's usually phrased that way, but I think that is a true statement. Cool. So we could use this information. We know that as cooldown gets bigger, price should go down. And so we could create our own little dumb machine learning model that basically says, pick some random price that CryptoKitties start at, and then for every minute of additional cooldown, you lose a little bit of value. So I wrote a function here called predict price that it takes in the cooldown as its input. And it says, we're going to create a variable B that is just like what I think a default CryptoCat costs. And then for every minute of cooldown, you're going to lose 0.01 Ethereum. Now, I just came up with these numbers. Don't put too much stock in this. But then in order to calculate this, we can say, okay, multiply the number of sort of the penalty by the number of minutes of cooldown. And then given this is negative, then add that to our sort of original default price. And that's our prediction. This, again, it's not a very good prediction, but it's what we're going to go with. And so we can apply that prediction function to our input data of clean speed, and we will get out a predicted price. So we can see predicted price here. Ooh, in fact, something that would actually be kind of fun to look at now that we've predicted prices is to actually graph our predicted prices versus our actual prices. So if we come back up here and grab all of our graphing stuff, we can, in addition to, so in blue, we'll plot our actual prices. And then maybe we say in red, and we'll make this a little bit denser but smaller. These will be our actual prices. So a couple of things should be clear here. One is that the it's not very accurate, right? We didn't actually place most of these dots next to most of the actual prices. But we do get a straight line because we just used the equation for a straight line, y equals mx plus b. Like that's literally the equation we wrote. But it does capture something. We place a lot of dots right around these dots, and we place a lot of dots right around those dots. And maybe there's something to that. Maybe. So we can actually calculate how close our predictions are. And this is actually the goal of our competition, right? Yes, y equals mx plus b, or c. You can use whatever you want for the constant there. That's actually an interesting thing. In early grade school, like in 7th grade, I was taught y equals mx plus b. But then once you get into calculus, you always use c as your constant when you add a constant to things. Which I don't know. Drop in the chat. Were you taught y equals mx plus c, or were you taught y equals mx plus b? We're really doing real math hours. This is a thing that I like to say sometimes is people ask me, oh, like if I'm bad at math, can I do computer science? I'll say like, hey, so much of computer science is math free. And then you get into like basically cybersecurity and machine learning. I mean, lots of computer science can use math, but it's like, oh yeah, once you get into sort of deep machine learning, you end up using a lot of math. Okay. So it looks like we see a mix. Some people are using. I wonder if y equals mx plus b is more common in the States. I don't know. It looks like we have an almost even split of plus b's and plus c's. That is a new thing that I learned today. Huh. Okay, so this graph, again, it's kind of interesting, but it doesn't tell us that much. Like, I don't really know how much, like how good of a job this really did at capturing our data. And we really want to get that one number. I mean, really, we want to get the number that is on the leaderboard, right? On our leaderboard, we have some score here, which is the average error. And we really want to calculate that. So the way to calculate mean absolute error is to first calculate our error. So to calculate our error, we can just take the predicted price and subtract the actual price. So here we get a bunch of error numbers. So none of our answers are really that correct. Data structure has so much of binomial theorem. Okay, that's true. Yeah. There's some binomial theorem. There's some math and data structures and like running time complexity. Yeah. Did I skip something? I didn't catch getting weights. So yeah, the weights that we picked, I just picked them basically randomly up here. I mean, I picked them so that they would kind of match, the max numbers that we picked. But yeah, these numbers are not really special. I pulled them out of my butt. So I skipped something, and we'll come back and revisit that assumption in a second. But so here we have our actual error, but really we want to get our absolute error, because if you took the average of this, like some things would be positive, some things would be negative, and it would average close to zero. But really being wrong in the positive direction is just as bad as being wrong in the negative direction. And so what we want to do is we actually want to get the absolute value of all of these things. So we can say NP-ABS, and it gets the absolute value of all of those individual numbers. Oh, I guess we got to import NumPy. Boom. And so then once we have our absolute errors, so absolute error just means you've removed the negative sign. Oh yeah, Darwin is down here. Yeah. I don't know if you could hear him or smell him. I can smell him. Or you just saw that I was looking down at him a lot. Hey, bud, you want to say hello to the people? Okay. Darwin wants to say hello. Hello, mister. Oh, hello, Mr. Perfect Boy. Say hello, Darwin. There's your daily dose of Darwin. Where were we? Isn't he adorable, though? Isn't he adorable? He is the most perfect dog in the world. So absolute error just means whatever our errors were without the minus signs, right? And then once we have that, then we can just say numpy.mean to just get the final average of all of our errors. And that is mean absolute error. So if we run this, we should get a number, 69.04. Nice. So if we jump back, this is actually a worse error than we got just by literally guessing 0 for everything, which is, first of all, kind of sad. But why is that? Well, let's look back up here. So many of our numbers are just down here, and we can draw a straight line, but that straight line is going to sort of be dictated by our extremes. And so it ends up with that we make a lot of predictions that are really far away from a lot of our answers. And so if you imagine the just guessing 0 all the time, that would just be a straight line at 0. And that would actually get kind of close to a lot of the numbers, right? So this is like one reason why this as a model is, at least as we wrote it, not very useful. Now you could say, well, hey, like we just picked bad numbers, right? You could pick a better slope and intercept, and you would get better results. And that's exactly what we should do. So we picked our numbers pretty bad. In fact, actually, so we're on average 69 ETH away, which I think I have this in the notes, is that to USD is like, okay, yeah, more than $100,000 off, right? So that's a lot of error. But we picked random numbers for M and B for our slope and for our default price and for our how much do you get penalized for each minute of cooldown. So our first idea for a machine learning algorithm is to let our computer try out a bunch of different values for our M and our X parameters, and to see which one has the lowest error. And this is exactly the idea behind linear regression. So I usually try to start most streams off with the first machine learning algorithm we talk about is linear regression. And so that's what we're doing here. So we basically just manually did a very bad version of linear regression, but now we can import from a library, import a very, very sort of polished version of it that does it very well. So sklearn, I'll take a second just to plug sklearn. So scikit-learn is a really, really nice collection of different machine learning algorithms. And as you're getting started in machine learning, it's, I think, one of the libraries I would recommend the most. You can honestly just come in and, oh, look at this. These are some things we talked about today. We talked about classification and regression and clustering, and we're doing regression today. And in fact, if you clicked on regression, I think you could probably find linear regression, maybe. Wait, sklearn linear regression. Come on. Okay, I don't know why it wasn't showing up on that page, but linear regression. And so a really nice thing about scikit-learn's documentation is that you can come in and see an example of using basically everything. So here they have you importing NumPy, they have you importing linear regression, they create a little fake data set, and then they show you how to use linear regression. Yeah, I think I was missing a space. So we will do that in the same way. We'll say from sklearn.linear model, import linear regression. Now, an interesting detail here is this is a linear model. And one of the ways that we see this is that even though our data was all over the place here, all of our predictions fall in a straight line. And so if you're making predictions and all of them fall in a straight line, that is a pretty good sign that you are using a linear model. And linear models are good for some things, and they are really, really limited for other things. And pretty quickly, we're going to outgrow our linear model. In fact, today is the last day we'll use a linear model. So we can create a linear regression model like this, and we'll call it LR model. And then to actually train our model, here, I'll put this in another cell. We'll say creating our linear regression model. And then to train it, we use the .fit method. So in the .fit method, we're going to pass it all of our input data and all of our output data. And one thing you'll notice is that our input data, we just have one column here, but we use square brackets twice. And this is actually maybe a nuanced thing about pandas that it's worth touching on. So when you have a pandas data frame, like our train df, so it is a table, or it's a data frame right now. And if you just grab one column, like say speed or clean speed, it gives you a series. This is no longer a data frame. It is a one-dimensional vector. It is a series. But if you want multiple things, such as clean speed and price, or clean price, you can, instead of just a column name, you can pass in a list of columns. And when you do this, the thing that comes out of it is still a data frame. This is still 2 dimensions, right? It still has columns and rows. Now, if you just want one column, but you still want it to be a data frame, and it seems a little bit silly, but this is technically still 2 dimensions, right? This is not just a vector. This is still a matrix. And if we remove those square brackets, then now it turns into a sequence. So that is why in your input, you have to include those square brackets twice, because you want to get out a 2x2 matrix. So we're going to pass in our input data and our output data. And this is exactly what we're talking about, is that we have labeled questions and answers, right? Our question is, hey, based on this speed, what should the price be? And the answer is the price. And so we pass our labeled examples into lrmodel.fit. And out of it, we get a trained linear regression model. So now that we have our trained model, we can actually use it to make predictions. Let's see, is variable.apply func same as func variable? So that is a great question. So specifically, there might be other applications of .apply, but specifically with, I'm not sure if there was a specific case where we did this, but specifically with data frames, more or less the answer is yes. So if we take, so here's sort of a good example, is we applied predict price. What if we just called predict price on clean speed? Actually, not predict price might be a bad example. Let's come up and do, is clean price? No, that's predict price. Let's scroll up. So there's a good question, is what is .apply doing here? Okay, so here's a good example. So clean speed, we have some logic here, and we're calling train df speed .apply clean speed. But what if instead of .apply clean speed, what if we just called clean speed, which is a function, and we passed it in train df speed? Now, in your mind, take a guess. What's going to happen here? I'll scroll up so you can see what I'm actually talking about. We run it, we get an error. And the reason is because this function is only written to accept a string, and we tried passing in a whole sequence. So what apply does is it's really kind of like a for loop. Apply really says, I'm going to run through each of the values inside of your column and call this function on them each individually. Whereas if you just call the function on that thing, it tries to take the whole list at once and run on it. And like, for example, you can't do a regular expression on a series. You can only do a regular expression on a string. I hope that clears up the distinction between just calling a function and then passing it into apply. But yeah, apply is an interesting paradigm. It really gets into functional programming, which, if you're not familiar with functional programming, it's a programming paradigm similar to object-oriented programming or procedural programming. But it is, yeah, instead of writing out exactly what you want to do, you define one function and then you pass that function to other functions. Not a great description of functional programming, but kind of. There are a lot of functions involved. Right on. I am glad that that helped. Oh, okay. But so now that we have our trained model, we can actually make predictions. So we can do. Let's see. Okay, yeah. So our LR model also has a dot predict, and you'll predict in just the same way that you trained, but you'll just leave out the price because in this case we're predicting as if we didn't already know it, right? So you can say LR model dot predict, and then we'll take all of whatever comes out of there. I mean, we can just call this in C, but it produces another list of numbers. So this predicts a number for each of our inputs. And we can assign that to our linear regression predicted price column. And so actually, before we calculate the error, let's hold that down there for a second. We can see what this looks like. And if we wanted to, we can graph this again. So we had our randomly selected points, our randomly selected parameters. But so what if instead of plotting against predicted price, now that we have some predictions, what if we plotted against our linear regression predictions? And okay, so this is super interesting. So this, it makes a different call. It's not saying everything should be 0, but it is saying, okay, what if we started a little bit lower? Because really these things, there aren't that many of them. And really I want to predict numbers that are relatively accurate for this giant mass of numbers. But then I do understand that on average, the price goes down over time. So still a little bit difficult to see based on this graph, but like I would guess that this would do well. I know it should do better because the numbers were chosen by an algorithm and not me randomly generating numbers. But it looks as though it has made a more reasonable trade-off between where do I predict based on where all the numbers fall. And so now that we have visualized it, also, does everybody sort of get the visualization here? Is that these are the, the big blue things is like the truth, and then the small red dots are sort of the what our guesses are for the truth. And because it's linear, it's like, okay, we're never going to hit all of these points, but we are sort of closer to the average point with these kinds of predictions. And so to recap, earlier, our error was 69 Ethereum. And then here, boom, our error drops down to 16. So that is like an insane improvement. That's really, really great. And it is a sign that the original numbers we picked were not very useful. We could dig a little bit, if people are interested, we could dig a little bit more into exactly how is our linear regression model sort of picking those numbers. But to a first order approximation, it's okay to think about it like the computer is just really quickly trying out a bunch of different numbers and seeing which lines produce the best results. Because it's very easy to check what your error is, and so you can just really quickly try a bunch of different values and then pick the one that is the closest, or that provides you with the smallest amount of error. Cool. So let's use this model to make a submission. And so actually, if we jump back over, we know that right now a lot of submissions we're getting 38 Ethereum of error, and we're down at 16. So this notebook should just blast through, and we should get some better results. So how do we make a submission now? Okay, so this is good. We can dive into a little bit more about the specifics of these files. So remember, we have a train file, and if we look at our train DF, you can see now we have lots of additional columns that we added, but the original columns were ID, price, speed, and image. But if we look at our test DF, we have all of those columns except for price. And so we want to basically, based on this column, this table, we want to generate the price column. And that is what will get us looking like our sample submission. If you look in here, it just has ID and price. And so we need to create a price column for test DF or provide predictions for what the price is going to be. Oh, also, we're way past halftime. So maybe I've teased how we're going to submit, but then we'll take a short break so I can drop the feedback form. Um, Getting the feedback is super helpful, y'all. It does really help me know if I am just going too fast for everyone, or if if most people are it's a good pace for you. And of course, the big thing is that it is the way that we are going to vote on what color glitter I have to wear on Friday. Boom. So here's the feedback form. Let me know how things are going. And I think that's the whole break. I'll take one more sip of water. This actually has been a great stream because I've both remained hydrated by continuing to drink water, and I also haven't had to pee yet. So that's gold, you know. Usually it's one or the other. It's either I'm dry by the end, or I have to get up and go to the bathroom. But we're threading the needle today, folks. We're threading the needle. So our test data frame has everything except for price, and we need to generate the price column. And so the first thing that we're going to do is we're just going to have to create that clean speed column. So if we just do this, we can see that in our clean speed column, we're now getting data that looks really similar. It's those nice integer numbers that fall at sort of regular intervals. Something that actually is kind of interesting to do is to visualize our test data. Obviously, we don't have the price column, but we can still visualize the speeds here. And a thing that's really, really great, a thing that's super nice to see, is that we have a similar shape to our histogram here as we did in our training data. If we come back up here, this is our training data, and it looks really similar to our test data. Sometimes you will get something called distributional shift, where your test data does not look like your training data, and if that happens, it's very, very sad for you, because there's very little you can do at that point to sort of save your algorithm if your training data just doesn't look like your test data. But thankfully, we are in a position where our training data does in fact match our test data. So now we can make a list of predictions and put them in a price column. And so we can make our predictions. And because we're on this nice little path of visualizing our test data, why don't we go and visualize PLP scatter our test DF clean speed versus our test DF price. Oh, not scatter. And obviously it looks a little bit different because we don't have the distribution is different. But okay, that's given us a line of data, y'all. Very good. So now, in order to actually finish this and make a submission, we just have to grab the relevant columns. So if you remember from sample submission, it just asks for ID and price. And so we just want to get ID and price into our submission data frame, and then use to.csv to print out a submission.csv. And we can pass index false just to make sure that we're not printing out any additional columns. And if we do that, it should pop up here. We have submission.csv. Unfortunately, you can't see your working or your sort of output files in the nice little rendered thing, but you can always download them and double check. And I imagine you can't see. Let's see. I never use numbers. If we zoom in, but yeah, we have an ID and we have prices, and that looks pretty good. And at that point, we should be good to clean up and submit it. So now that we have written a submission.csv file, we can click submit, and we should be off to the races. Oh, wait, you know what I just realized? Oh, no, we should be fine. Yeah, that should be okay. So if you click over here, you should be able to see the submission. And interestingly, our error is higher than we might have expected. And let's talk about why. Latest score is more off. Yes, you are absolutely correct. So our error is higher. Now, so an interesting thing that we can look at is when we ran our model on our training data, how did we do? We got an error of 16, right? But then when we ran our training data on the or when we ran our model on the test data, we got 42, which is even worse than just picking 0, apparently. And so you might ask, well, hey, why is this? And the sort of the simplest answer just gets to the fact that that when you're testing your model on data that it has already seen, it has the ability to kind of cheat, right? Like it was memorizing some specific things about the training set that were not necessarily true about the test set. So of course we did notice that that up here, or no, we did notice that the distribution of cooldown rates was similar, so that this histogram looked similar to this histogram. But that doesn't necessarily mean that the relationship between those those things is the same. I mean, to prove this point, up here, it's like, well, we have one giant cluster here and one giant cluster down here. And knowing how many of our CryptoKitties are sort of in this 0 column right here doesn't really matter if we don't know how much of them are being sold for 100 and how many of them are being sold for between 0 and 20. And so this is, I mean, it's easy to sort of throw up our hands and be like, it's you know, the test data is just on some fundamental way different from the training data in a way that the information that we have can't capture, right? We would say that in this scenario, our model has failed to generalize. And there are a couple things that we could consider doing about this. One is we could think about making our model, giving it additional capacity. Usually giving your model additional capacity in linear regression means giving it additional columns. So like one classic thing that we could try, and because we actually have some more time, we can just try it now, is you can, because our model inherently can only capture linear relationships, you can include nonlinear transformations of your input data. So in our scenario, speed is just a singular number. But what if, I mean, we noticed that speed has sort of a nonlinear growth pattern, right? It doubles every time you go up a level, you double how long it takes you to go down. And so you could imagine, what if we added the natural log of speed? That might be like an interesting additional feature to look at. So like, let's give that a shot. Let's see. Let's write here, say, creating a model with natural log of speed. Now, if you're unfamiliar with natural log, a similar way to think about this is like you could also include the square root of your data. In fact, actually, I think natural log makes more sense, but just because square root is more accessible, let's say square root of our data. So we right now have one column in our training DF and our test DF called speed, or clean speed. Boom. But we could generate a column of all of that square rooted by just raising it to the power of 0.05. And this gives us another interesting number that is importantly non-linearly related, right? If instead of saying raised to the power of 0.5, if we just said multiply by 2, there'd be literally no purpose in adding this because it doesn't do anything for our model that our model can't do for itself, right? If you add something and then you add 2 times that thing, that's the same kind of operation that our model was going to learn to do anyway. And so us doing that for it doesn't actually help. But what we could do is we can say, take the square root of it and call this root clean speed. And then we could add this to our training data set as well, our testing data set as well. And so we get another, so this is exactly adding another feature. Now, before we do this, I want to say, I think it's an interesting thing to try. In this scenario, based on the fact that we were doing really well on our training data and doing worse on data we hadn't seen before, I don't think this is going to help us. In fact, I think it is possible it could hurt us. It might help a little bit. It's hard to say in this scenario. So we can say root clean speed. And then let's try to train a linear regression more features model is equal to linear regression. And then we'll train it on our training data. So we'll say both clean speed and root clean speed is our input, and then our output should be clean price. And we could start by making predictions just on the training data to see what that looks like. So we're just giving our model sort of additional information to use in its decision-making process here. And let's assign this to train df more features prediction. And so now if we wanted to, we could do our same visualization up here, only instead of comparing it to our basic linear regression model, we can compare it to our even better linear regression model. Okay, cool. This is great. This is what I'm hoping for. So you can see that before, up until now, we could only get a straight line. And because we gave our model some nonlinear information, it is able to represent a relationship that is itself nonlinear, right? We gave it the square root of our data. And so now it is doing something a little bit different. And it is actually saying, okay, maybe you start here, but then as you get a little bit slower, you actually curve up, and then you slowly start to curve down. And it's sort of making that sort of trade-off, which I think is just interesting that is the relationship that it sort of learned to guess. I can't necessarily say anything about like, is that better? But the fact that we have left the sort of linear realm and we now have a non-linear relationship is kind of cool to observe. So now we can do that same prediction on our test data set. I actually just copy this whole thing. And we can say, instead of train df, we can say test. And instead of more features prediction, we can just call that price. And we'll be predicting based off of our test data. And we wrote a submission file. So before we got 42, let's try it with this. I will again say I haven't tried this before, and I am not. I mean, I might be surprised, and it might be better. It's totally possible, but I'm not like confident that this is actually going to improve. I'm confident this improved our error on our training data. In fact, actually, while we're waiting, let's calculate. We visualized it, but let's calculate our error on our training data. So we have our little snippet of code to calculate error, and after doing this, let's just find out what our error was on our training data. With more features prediction. So it went from, what was it? It was 16 point something, and it went down to 16.5. It was 16.56, and now it is 16.52. So it went down, but just a very, very little amount, right? We just got a tiny bit of additional performance by adding that column. But it looks like we submitted. Let's see what happens. And yeah, it basically doesn't change. In fact, it made it just a little bit worse. And this is super interesting, actually, that we gave our model more power, and it got a little bit better on predicting things that it had already seen, but it got a little bit worse on predicting things it had not seen before. So I think that is where I want to leave this for today. We have messed around with some linear models. We technically made the model nonlinear by adding the square root of that thing. And we sort of got familiar with our method of calculating our error, our mean absolute error. Tomorrow, we're going to, I guess the big headline for all of this is this was sort of a basic session to introduce you to machine learning in general and linear regression and the idea of our training and our test set. But most of the power here is going to be from our images, right? Because we only used one little individual item, where our images technically have like tens of thousands of pixels, right? Our images have so much data in them that we can train our model on. It's going to be sort of more powerful for generalizing and making additional predictions. And so that is what I'm very excited about, and that's what we're going to tackle starting tomorrow. We're going to resize our images. We're going to look at Keras. We're going to look at dense neural networks. We might get to convolutional neural networks tomorrow, depending on sort of the speed of things. But I think on that note, let's just recap, check back in with the competition. I don't imagine our leaderboard has changed. So something you should know is if you we have some entrants down here at 42, 46. Is that if you submit 2 different submissions and one of them gets a higher score, Kaggle will just pick the one that is higher. So don't worry about trying things and getting them wrong. Because Kaggle will let you just say, yeah, whatever my highest scores are, those are the ones that I want to count. We have 18 submissions now. That's incredible. Discussions. Why image on CSV has dots and images files don't? Yeah, it's a good question. Yeah, so this is even before I launched the competition. This is actually a thing I was aware of, which I'm very, very confident that Marilia is not on this stream. But yeah, this is we'll explore this tomorrow. Oh, interesting. We got some more notebooks from Marilia. Discussions, if you want to join in and get your contributor status. So you can leave a comment down here. Great question. When they're the same score, how is Kaggle differentiating between them? This is a great question, and the answer is I believe it is whoever submitted earlier. So if 2 people got the same score, whoever got that score earlier is considered sort of higher up. And this is, I think, because oftentimes if you submit something and you get a high score, but then you publish your like the way you did things, they don't want to penalize you for sharing. And so if you get a really high score and then you publish it and share it, and everybody else uses your notebook and just gets the exact same score, you would still be sort of on top. The hope is that by the end of this week, we will have sort of more spread, and there will not be everybody, everybody in the 17-person tie. This is, I'll admit that because I usually do 3 or 4 sessions in a week, and this week I'm doing 5. And so it's like, oh yeah, we've got 3 whole more sessions to sort of dig into this more. But I do hope folks stick around. How do you validate your account in order to make your submission count? This is a great question. So if you, are you asking how to become a contributor and get sort of the updated little profile, or is this something about like I believe there is account verification just to like click an email. So you have to use a valid email address and then go into your email and click the verification email. If you're having trouble with that, I'm happy to help debug. Otherwise, if you're talking about how do I become a contributor, that is a great question. And if we just navigate. Sure, let's navigate to me. And you go to my profile and you click on that little thing. So this is the Kaggle progression system. And if you scroll down, novice, everyone starts out as a novice. And then to become a contributor, these are the 4 things you must do. Run 1 notebook or script, which at this point, everybody follow along should have. Make 1 competition submission, which again, at this point, everybody should have. Make 1 comment. So if you just go and comment on the discussion or create your own discussion, you'll get your comment, and then give 1 upvote. So upvote either the discussion topic or a notebook or one of our fellow hackers' comments. And you can get your 1 upvote. And then after you do those, it might take, I think sometimes it can take a delay about like an hour or 2, but you do sort of get the contributor status. And that is how you become a contributor, if that's what you were asking. If it is like oh, how do I click the verification email? That's different. Me, Mr. Mustard asks, question, I think you mentioned TensorFlow earlier. Are you going to go into that at some point? Yes, this is a great question. And the good news is that for the rest of the week, we're just in TensorFlow. So I think I mentioned this, I think at the beginning, there were The first 2 days are pretty beginner friendly, and then the last 3 days we sort of pick up the pace a little bit. So we'll be getting into Keras, into convolutional neural networks, and the like. And yeah, it should be a good time. If there are any other questions, I'm happy to field them. Otherwise, I think I will sign off, and we will call it a night. And I will see you all back here at the same time tomorrow. So I will stall for just another minute. I'll play you out on Kalimba. So if there are any other questions, I can answer them after our song. But as always, thank you so much for being here. It has been a blast, and I'm excited to see you tomorrow. Oh, actually, it looks like there are no other questions. But before I leave, I'll just one last time drop the feedback form and the registration form. But thank you all so much for being here. Be sure to both check in so you get credit and fill out that form to let me know how things went and vote for what color glitter we're going to be doing. But thank you so much for being here. Happy Tuesday and happy hacking, y'all. Bye.